So in this tutorial, we are going to pick up on our concept of conversation about converting mass and energy and the equation E equals mc squared. We've talked about annihilation of matter and antimatter and how much energy it can produce. Now we're going to pick up on focusing on nuclear fission and nuclear fusion. Before we can get to that, though, we want to introduce two new units of measurement for the world of the small. One is the atomic mass unit, something you should be familiar with from chemistry. The other is called an electron volt, which is a very, very small unit of energy. We're not going to do much with the electron volts, but it will come up in our final answer. So to give us a context for this, since the last process, very often the mass to energy involves nucleus to atom, it is much more convenient to express masses in other units of other than kilograms. So the preferred nuclear unit of mass is the universal mass unit, which is given a U. And by definition, it's 1/12 the mass of a carbon atom. But that's not anything we have to worry about right now. Also, since energy is involved and it's really tiny, we need a small unit of energy, and we're going to introduce what's called the MeV. The capital M stands for mega millions of electron volts. An electron volt is a really small number. It's like 1.6 times 10 to the negative 19th joules. So it's a really tiny amount of energy, but we don't need to know about that. Okay, so the idea is if I express the mass of some objects in atomic mass units and I want to convert it to energy in MeV, there's a simple conversion number. And this conversion number is found in your reference tables. It's on the very front, fourth from the bottom. And what you need to know, and what I'm going to write here is what's in your reference tables, that one atomic mass unit of mass that is converted to energy is equal to 931 MeV of energy. Okay, so let me say that again because that was kind of awkward. 1 AMU of mass, not 1 kilogram, but 1 AMU of mass is equivalent to 931 MeV of energy, which is not a whole lot of energy in terms of joules. It is roughly 10 to the negative 13th joules. But at the level of nuclear reactions, this is what we most often talk about. All right, so now let's apply this to the idea of nuclear fission and fusion. So what's the difference? Fission, which is associated with the nuclear bombs that we often see in movies, television, documentaries, is nothing more than splitting large nuclei into smaller daughter nuclei. And you get a lot of energy out of it. Okay? And what's literally happening is if I take a heavy isotope, uranium-235, and I send a little bullet at it, if you will. That bullet is neutron. And what it'll do is it'll cause this split into two smaller nuclei. You don't have to know what they are, and a bunch of other neutrons. What is critical about this, what makes it so important, is not only do I get this X, I get plus extra energy. Energy is released in this process, and we want to understand how much energy is released. So where does this extra energy come from? Well, what we're going to look at is something called mass defect, which basically is a way of looking at, if I take the total mass of what I started with and I subtract off the mass that I end up with, I will find that it's not zero. They're not equal masses like you'd expect in conservation of mass. We have, in fact, lost mass. And so the amount of mass lost goes towards the amount of extra energy that I put up here a few minutes ago that I erased for some reason. Okay, so we want to calculate the amount of this based on the amount of energy or mass that's changed or been converted, and a key component to that is this conversion factor up here. Okay, so we're going to look at the masses in terms of AMUs. So what I'm talking about with this mass defect is the mass of the U-235 minus the mass of the neutron, or plus the mass of the neutron, that's what I started before, minus the mass of all the products. Okay? So that's what delta M means. All right, so let me do that in the space below here because I've run out of space there. So what this would be is I've got the mass of U-235, which is 235.0439, okay, plus the mass of a neutron, which over here is 1.0086 U's. Okay, I'm going to put parentheses around that. Minus, all right, my product. So when my first product is xenon 136, so its mass is right here. 135.9072 plus strontium 88, 87.9056 plus 12 neutrons. So I could do 12 times 1.0086, put double parentheses around that. And you got to punch those numbers in your calculator. If you do that carefully, you will find that the difference in mass, or the mass lost in splitting uranium-235, is a very small amount, 0.1365 atomic mass units. Okay, so every time you split a U-235 atom, that's how much mass has been converted into energy. And that's not a lot of mass, but if you do that with enough nuclei, you can get a tremendous amount of energy. So now let's calculate the extra energy in MeV. Well, we know 1 U of mass loss is 931 MeV. So in this particular problem, our delta M, so our energy is going to be 0.1365 U's of delta M from down here, multiplied by 931 MeV per U. And if we multiply those together, we get a roughly 127 MeV. Okay? And that's how you do that. Now again, that's not a whole lot of energy, but if I were to do this for a whole mole's worth of uranium, which is a measly 235 grams, I would get a tremendous amount. I would get roughly, let's see, if 1 MeV is 10 to the negative 13th. This is 110 to the negative 15th. Okay, times 10 to the negative, I get roughly 10 to the 9th joules. I might have done my math a little bit off there, but it's a tremendous amount of energy. So that's why we can get a lot of energy from an atomic bomb, because of that conversion. Okay, so the next process we want to finish up with is fusion. Fusion is the exact opposite of fission. Okay, it's a combination or combining of light nuclei to make heavier nucleus, plus extra energy. And as we talked about in class, fusion is ideal because we can get a lot of energy for fairly little mass, and is very little pollution, okay? So the products of fusion have more energy than the initial reactants because mass was converted to energy. The most common fuel for this are isotopes of hydrogen. One is called deuterium, which is given a symbol H2 because it has a mass of 2. And the other one is called tritium because it has a mass of 3. This is given a symbol capital D sometimes, and sometimes given a capital T. So let's look at it. Typical fusion reaction that might occur in a research vessel. I've got deuterium fuses with tritium, and what I get is helium, He4, and a neutron, plus energy. And it's that energy that we're interested in. Okay? So in order to find the amount of energy, we need to first find the mass defect once again. Okay, delta M. So we have a table here to the right, which gives the masses of each part. So let's plug them in. So again, our reaction is deuterium plus tritium gives us He plus a neutron. So deuterium 2.0141, tritium 3.0160. All right, all those are in atomic mass units. Minus 4.0026 plus 1.0086. All right, you should do the math on your own, but I've already worked it out. So our mass defect is 0.0189 U's. And if I multiply that by 931 MeV per U, I get the amount of energy that's given off, and that's about 17.6 MeV of energy. Okay? And I presented this in a PowerPoint. If we had a hypothetical fusion reactor that burned at a rate of roughly 15 10,000ths of a gram per second, and we want to put out a certain power, a coal burning power plant would need to be burned rate at around, I think it was 70 grams per second, which is a large amount comparatively. And if we had a train load of coal, that would burn through this fuel in around 1 hour, whereas if we had these pellets of deuterium and tritium, it would take about 7 years. Okay, so huge upside to trying to gain energy from fusion reactions. There's a tremendous amount of energy available. The products have no pollutive value. There's not greenhouse gases. They're not radioactive. They're not dangerous. There's plentiful of this fuel. The major downside is we need super high temperatures in order for this to occur. We haven't been successful yet in being very efficient in achieving those. Okay, so that concludes our discussion on fission and fusion.